Okay, are we live? Yes.
There is a live symbol
I think so. We are. Okay. Good. Okay. Well, welcome everyone. So this is the first session, opening session of the QIP virtual session on Friday, and we're going to have this is a 50-minute talk with some questions, maybe about 5 minutes, and then there will be you'll see that there's another session right after, which is a live Q&A session with Thomas. So if you have further questions, you'll be able to join that. I'm going to suggest that if people have questions during the talk, that they put them, rather than in the Q&A, they put them in the chat. And that way, if you have a question, feel free to ask it, and then other people can, in the chat, can answer. And if there's a question that other people can't answer, then we can always, I can always pass it on to Thomas, or Thomas can also monitor that a little bit. Okay, great. So it's a pleasure to have Thomas Monz from the Department of Experimental Physics at the University of Innsbruck. He's also the CEO of AQE. And he's going to be talking about experimental demonstration of universal quantum computation with logical qubits.
So good morning, good afternoon, good late night for some of you. First of all, thank you for having me and allowing me to give a presentation on some of our work with a trapped ion quantum computer and the push forward to really demonstrate universal quantum computing with logical qubits. And so my presentation is roughly ordered by giving you a little bit of a primer motivation on fault tolerance as a circuit property, so that you can make sure that error don't propagate uncontrollably across your register. I'll then derive from that theory essentially challenges that we need to overcome experimentally in order to make sure that whatever wishes our colleagues have from the theory department to implement them on the devices, how we can address these requirements with our trapped ion quantum computer, and at the end, how we combined everything to then make sure that it actually works on our devices. And so here, the first thing, because I know for some of you it's 3 o'clock in the morning, so if you fall asleep, hopefully you won't, but if you fall asleep in say the next 10 minutes, I'd like to start with the takeaway message right away. And so the takeaway message is, as we grow our quantum computers, aim for more and more qubits, we have to have error correction. But unless we have a universal logical gate set acting on those logical qubits, it doesn't help us. So we really need to push for this universal gate set. In order to achieve that, we have to have fault-tolerant circuits and design them that way that the errors don't, let's say, explode. And one very, very convenient way to ensure that the error rates don't A, explode, and B, propagate in an uncontrolled fashion is to use these flags, which various theorists came up with in the last years, to make sure that we can post-select for uncorrectable errors and make sure that error correction still works. Implementing these flag-based fault-tolerant circuits in principle is actually really, really challenging. So besides the typical requirements in terms of high fidelities and so on, you also need to have highly connected quantum registers. You ideally would like to recycle some of the qubits and so on, but all these requirements, that we are working on, these are all fulfilled in our ion-trap-based quantum computing platform. And that's why I will then at the end say, because we fulfill them and because we complemented and implemented everything, that's why we managed to achieve this. And so for the colleagues in the US at 3 o'clock in the morning, we did it, and I'll happily show you the rest now. So why am I and colleagues working in quantum error correction? So we have a history, both in terms of experiments and theory, to work on quantum computing, quantum error correction, because it's what we need. It's one of these, say, thick boards where we have to drill holes. It's not easy. It's not just adding yet another small algorithm proof of principle implementation, but these are one of, from our point of view, bigger challenges. And one thing that I really think is adamant there is that we need to have a tight collaboration between theory and experiment. And if you manage to have colleagues whom you can talk with, that really help you out, where you exchange the theory ideas with the experimental capabilities, and bring them together, and both sides understand and see how you sometimes have to give a little bit or push a little bit, then we can achieve, from my point of view, great things. What you can see here is some of the theorists we like to work with in the context of error correction. It's Markus Müller, who is now in Jülich, or Nico Fries in Vienna. And with these, let's say, collaboration with theorists, we have, for instance, started working on the repetition code with 3 qubits. Now, already more than 10 years ago, we've been working on the first logical qubit using the color coding with Markus Müller in 2014, and recently with Nico, we've been working on lattice surgery in 2021. But all of that were like the building stage for us on the experimental side with Philipp Schindler and myself to then push for, we need to have this universal gate set. And so if you talk about error correction, universal gate sets and so on, you could have a qubit, and in our case, it's calcium ions, but it could be anything else. It could be photons, neutral atoms, superconducting circuits. And essentially it branches off in 2 directions. You could say there's error protection or error avoidance. You think about the difference-free subspace, or you can think about implementing error correction per se, where you try to do measurements in between, figure out what's wrong and correct for it, and have some feedback cycle to really correct errors on the fly. We're pushing for that. So we, for instance, realized difference-free subspaces already like 15, 17 years ago. Subsequently, I have realized a universal gate set on the difference-free subspace already in 2009, while Philip was pushing, for instance, for error correction with reset and so on in our devices a couple of years ago. But then Markus, as I said, tight collaboration with theorists. It's like Markus Müller said, like the repetition code, look, it's not what you want to have. The thresholds are not good. Implementing gates might be challenging. Why don't you push for topological codes? And honestly, in the beginning, and beginning, that means almost 10 years ago, we were like, what do you mean with topological codes? What are they? Why should I care? And so topological codes, let's say the Pullman's version is, you would try to encode quantum information in a significantly larger system in such a way that errors which are small, and small means, for instance, they are local only, so they act only on 1 to 3 qubits and not on the full register, and they happen rarely enough. If these requirements are fulfilled, then these codes provide you the means of really suppressing and correcting for errors. And so Marcos said, like, can you implement that? Marcos at that time went to Madrid to work with Miguel Angel Martin Delgado, and they were looking into how can you implement color codes with trapped ions. And so we said, okay, what's the short summary? So essentially what you do is you have stabilizer codes. Usually you can draw them in, for instance, 3 colored lattices. The qubits would be sitting like these white circles here would be sitting on the vertices of these lattices. And you can define independently X and stabilizers on each of these plaquettes that allow you to independently both detect either X or Z errors, but also correct these X or Z errors. And as long as errors are sufficiently local, for instance, only here or only 1 packet, but never ever the full system, then you can correct for that. And you see the theory work has been, it's 15 years ago now. In principle, people like say that the theory was there, but we said, like, again, give me some advantages. There is, for instance, a surface code and so on. The short summary is the color code is more or less as good as the color code from our point of view. The thresholds are very comparable depending on which noise model you assume and work on. And so we said, okay, we know from the experimental side the circuit noise, we know the system, and we can now work towards full-blown larger logical qubits. And one thing where Marcos really managed to hook us towards the color code was the question, like, how can I, if I encode on this color code a logical qubit, how do I do gates? At the end of the day, there might be Jonathan who says, now let's do a Hadamard gate, let's do a CNOT gate on this logical qubit. How would you do that? And so we then learned on the color code, all the Clifford gates can be implemented in a transversal fashion. And that means when you want to have a Hadamard on your logical qubit, which is denoted here as 0 with an L as an index, all you have to do is implement the Hadamard on all of the individual qubits. And that's experimentally rather easy. And then we said, okay, if that applies to all the Clifford gates, then we have like 90% of the work done to get some logical qubit work going. And it also works with the CNOT, which belongs to the Clifford group. And one neat feature which we then saw was, well, because you do a CNOT between the first physical qubit of the first logical qubit towards the first physical qubit of the second logical qubit, you also see that errors actually just don't spread up all over the place. If I have a qubit error here, it will remain a single qubit on my first logical qubit and will a single qubit error on my second logical qubit. And because it doesn't explode, it's easy to correct for it, and that's why, for instance, the color code has this high threshold for errors. And also for us experimentally, again, that seems to be relatively easy to implement. So we said, Marcus, what's the smallest instance? Show us. The smallest instance here is 7 qubits. You can define 3 plaquettes. And on each of these 3 plaquettes, you define, for instance, the X and Z and X stabilizers. So you end up with 7 qubits. You have 6 stabilizers on that, which means there's a subspace for a single logic qubit for you to encode information. And 7 qubits, that's something where it's like, okay, that sounds easy enough under quotation marks. Let's try to work on that. And we ought to be able, because it is distance 3 code, we ought to be able to correct for any single qubit error that happens in that system. How would we implement it? Okay, back in those days, we had the 7 qubits and we had entangling gate operations where we can entangle 4 qubits at once, which was nice. So we said, okay, let's start with 7 qubits. We can decouple 3 of them and then do an entangling gate operations on the first set, on the first plaquette. And then you subsequently do this 3 times and you're done, and you end up with your logical qubit. That's what we did. That's what we then pushed for. We had that system. We then wanted to look into errors. And just here as a, let's say, reminder or primer, how does this error detection work? So ideally, all these stabilizers are meant to be in +1. And if they are in +1, essentially you would say, okay, all 4 qubits in that plaquette agree that they are in the correct state. So if all of them are in +++, okay, there is no error. Now imagine you do the stabilizer readout, and for some reason, the green plaquette tells you there's a -1. And so you could say, wait, if I look at that system, which error, like which qubit could have an error, so that the blue one says everything is fine, the red one says everything is fine, and the green one says something is wrong. And you will notice only qubit 7 is the only qubit which is not connected to any of the other plaquettes. And so you could infer then, okay, wait, my Z stabilizer says something is wrong, so we know my X stabilizer says something is wrong, so the Z error happened. And the only way for the syndrome to say only the green one says something is wrong, it has to be qubit 7. And you can repeat this exercise and really know then, okay, I can nicely map from all the X and all the Z stabilizers onto the individual errors. We did that, but in order to do that, now from a theory point of view, your readout of these stabilizers needs to be really, really good. You don't want to have any false positives and so on. And good means you have to have, like, say, readout errors at the 10⁻³ level, 10⁻⁴ level, ideally. When we did that now, there was one thing that Miguel Angel and Marcus were not so happy about, because we were using 4 qubit gates acting on this entire register at once. But if there is any error in this gate, suddenly all 4 qubits would be wrong, which means in terms of an error would be a 4 qubit error. We couldn't correct for it with that code, or let's say with the size of that register. We'd have to have significantly more qubits and so on. And so they said, like, you'd have to look into a different way of doing this. And so they said, like, well, how do you want us to implement it? And so Marcus was working then on fault-tolerant constructions using flag-qubits, and amongst others, like I'll mention some more theories. But so then Ben Reichert was working on these flag-based qubits for fault-tolerant constructions. And what you can see here is, for instance, 7 qubits. In a non-fault-tolerant fashion, you would prepare your logical 0, and you can see here 0 is what, like with the L, is the logical qubit, and the index of NF indicates that it's non-fault-tolerant. And then with just a minimal instance of using 1 ancilla qubits and 3 CNOTs, what you can do is you make some checks, and with that you can infer whether 2 errors occurred, which you are not allowed to have, because then everything breaks down. And so you start with this non-fault-tolerant fashion, you add this verification step, you can do essentially filtering post-selection on this flag qubit, and then just in the usual fashion, you can apply any Clifford gate on that system in a transversal fashion. And that's something where we said, okay, looks good, but we have to have a couple of CNOTs. In addition, what you can derive from that, one of the experimental challenges is, well, you have to have, first of all, good gates, which means ideally close to this fault-tolerant threshold in terms of fidelities. But now we also talk about it in terms of a circuit property to say you don't want to have any crosstalk, which means if I apply a gate here on the third qubit, I don't want to have it accidentally coupled to the second or the fourth, which induces additional errors. Ideally, there wouldn't be a crosstalk, the fidelity should be rather high. But again, it's not enough, so I want to bring up some additional research where some of that was even before Ben. So that's, for instance, Chamberlain and Goto, who were working on not only this flag idea, but also how do you generate magic states? Because the Cliffords are not universal. You have to have this magic state and T-gate injection to really turn it into a universal gate set. And so what they were working on already, as you can see in 2016, was work like, okay, you start with a non-fault-tolerant encoding. Now you want to make sure that you do something like, let's say, a Hadamard on that system. You need 2 additional ancillars to essentially check that it's the right state. And then you add some more error detection. And I think what I really want to point out at this point is, look at this single qubit. This qubit here connects to 7 qubits at the top, plus an additional qubit at the bottom, which means you'd have to have a high connectivity of 1 qubit being able to talk to at least 8 other qubits. And the other thing which you will notice here is that we've a couple of qubits here and there, and ideally you want to be in a position where you can recycle these qubits and not just always add yet another ancillar, but say it's measured, I can potentially reset and go on. So from that point of view, you could say for the experimentalist, you'd have to have 2 more challenges. You have to have a connectivity in your quantum register that at least one of the qubits can talk to 8 other qubits, which many of the current platforms can't support or they don't support. They could in principle. And in addition, it would help a lot if you could do in-sequence measurements, because you look at that sequence, you start off with the state, you first check for the Hadamard, and subsequently you do some more error detection steps. So you have to have this in-sequence detection as well, which is easier or harder for different platforms. And finally, you'd have this magic state. All you'd have to do now is inject this state into this other qubit. But if you look at the circuit, again, you start with your magic state, you do error detection, you just then essentially teleport it onto the next qubit where you start off again with a local one and you do some Hadamard. But if you count the qubits, you need to have at least 16 qubits. If you can't do recycling, this number grows up significantly more. And with that, somehow you see, from a theoretical point of view, if you go to any kind of device, you would say, well, there are at least those 5 challenges that you ought to be able to address to start to make sense to try to implement these respective codes and universal gate sets. And ideally, this works. So there's the lon-trap platform, which was pioneered in 1995 by Peter Soller from a theoretical point, and then Rainer Blatt was one of the first ones to start to implement it together with colleagues like Dave Wineland at NIST. So what you can see here is we use essentially a couple of metal electrodes and radio frequency fields. We store ions in the center by using these electric fields as a confining potential. We can use laser beams to individually address these ions and apply both local gate operations as well as entangling gate operations. We can look at these ions with a camera from the side, and for instance, each of these bright dots corresponds to an individual ion, and if it's bright, it's for instance a 1. If it's dark, you can call it a 0, and we can conveniently work in that system with up to 50 qubits, as you will see in the following slides. So how does this bright and dark work? Essentially, you have a ground state, you have a couple of excited states, and one of the excited states is a metastable long-lived state. So in this case, calcium, the state has a lifetime of about 1 second. What we can do now is we can probe the state of the system by sending light in on another transition. If the electron is in the ground state, we would excite it, it would start to decay, we excite it, it decays. The lifetime is only nanoseconds, so we have megahertz-ish scattering rates in terms of photons. If we now look at that at the ion with either a photomultiplier or a camera, you would get a high count rate if it's bright and essentially completely dark if it's in the excited state. And the coupling to this long-lived excited state usually is implemented with some narrow line width laser. So you can say if the lifetime is on the order of a second, the laser ideally has a line width of 1 Hertz. Previously, such a system was, let's say, academic selected devices with a few labs worldwide only that had such good narrow line width lasers. Nowadays, actually, these are available as commercial products from certain companies. And so that's like our 0-1, that's our qubit, where we encode information here, and we can also then do entangling gauge on such a system. So this detection, now we slowly try to make this connection to the theory challenges. How well does that work? So you can think of it, if the ion is in the dark state here, we don't get any count. Well, we shouldn't get any count. Essentially, it means there is always a little bit of stray light, so there will be very few counts, which you can see here. It's like if your ion is in the dark state, there will be a few dark counts, for instance, from your photomultiplier. And if the ion is in the bright state here, with, let's say, using a rebumper, you would have, for instance, mean count rates on the order of, let's say, 70 counts in 3 milliseconds. And you can, for instance, put a threshold there to nicely distinguish between these two states. And that works rather easily on the level of 10⁻3, 10⁻4 to distinguish the bright state from the dark state. And in that sense, this first challenge that we have initially set to say, you want to be able to read out your quantum registers with really, really high fidelity, that is already addressed with the ion trap platform. And how does such a system look like in real life? So here you can see, for instance, one experiment that we have in Innsbruck at the Academy of Sciences. Usually you fill up, let's say, 50, 70, 80 square meters of lab space, where the ion trap processor is actually this little vacuum chamber over here. Most of the lasers can be found here and there, and the entire control, computer, electronics, and so on is here, plus some additional supporting electronics up there. In the long run, this is not convenient to work with, essentially, as we want to get more larger and better systems going. So we then put an engineering effort into that. And here you see a device that we did in Innsbruck under my umbrella in the context of the European quantum technology flagship. So everything you saw on the previous slide, which was like a lab space of close to 100 square meters, now is 2 19-inch racks with 2 square meters footprint, and the entire device is powered from a single wall-mounted power plug. So we routinely can address single ions, both in terms of local operations. We can do the same thing with entangling operations on any subset of the qubits with typical error gauge fidelities on the order of 99%. The lifetime, as I mentioned before, is on the order of 1 second. The T2 time is on the order of 100 to 500 milliseconds. We demonstrated 24 qubit GHZ states. And one thing that helped us a lot also in the context of this project was that we pushed forward, let's say, standardized control capabilities. So some of you might be familiar, there are these, let's say, more and more established quantum software development languages or kits, such as Qiskit from IBM, Cirq from Google, PennyLane, PyTicket, and so on. And we support all of those, so that theorists doesn't really have to learn, let's say, the local device lab slang, but in a unified language, they can send us code and we can execute it on our devices. In addition, this device is not just small and high fidelity, but we pushed a lot towards automated control. So most of the control can be done with a push of a button to make sure that the fidelities are maintained. So how well does that work? So here you see, for instance, an ion register with about 50 qubits, where we move the beam from left to right, and you can see the excitation of the individual ions. And as well as you can see here is that the leftmost and the rightmost ion, because that's essentially how far we can move the beam, then slowly starts to couple worse. But we have reasonable control on all these 50 qubits in our register. For instance, we can characterize the system in terms of crosstalk. So if you want to address one ion, how much light leakage do you have to the neighboring qubits? So we define that as the ratio in terms of Rabi frequencies from the neighboring qubits compared to the address qubit. That's why you don't see anything on the diagonal, because that's where the light is meant to be in the first place. And then all the other qubits here are color-coded with these ratios. And as you can see, these numbers are all relatively small, but actually we can play some tricks. We can do some error suppression, for instance, similar to the devices and ideas that are also, for instance, developed by Mike Biersack in Australia to further suppress these undesired coupling to neighboring qubits. Here we did it in context of 10 qubits. And you can see we can suppress the undesired coupling to next neighboring qubits in terms of Rabi frequencies to the 10⁻⁴ level, which means in terms of error rates, that's actually at the 10⁻8 level. And that means at this point, we more or less can neglect this crosstalk on the local operations. Finally, how good are the 2-qubit gates? So what you can see here is some work that we just did quickly was like take a 2-qubit register and we can pick any subset of 2-qubit gates acting on this 12-qubit register. And we see that we have fidelities on the order of 99%, regardless of the subset that we pick. And in that sense, we have shown that we have both a good gates, but on the other hand, we have also negligible crosstalk. That's exactly what you want to have in order to, let's say, get close to these fault-tolerant requirements in terms of fidelity, but also to then look into circuit properties. And finally, one of the requirements was also we have to have high connectivity. So what you can see here is, let's say, standardized tune-up routines that we are using, where we look at applying an MS gate, which is disentangling operations in our process. So it's an XX operation. And we now implement it between qubit 1 and 2. And we, for instance, check how much leakage there is, how much phase shift there are on the neighboring ions. And you see here we characterize it for 1 to 2, 1 with 3, 1 with 4, and so on. That's why this white structure looks this particular fashion. But it also nicely demonstrates you in this case where we are looking into that, is that we can also have a fully connected register. And so this requirement of having 1 qubit talk to at least 8 other qubits in the register is also addressed. Then next requirement, again, we want to do error correction, which means we need to measure in the sequence, which means you encode your logical qubit. At some point, you say, check the stabilizers, tell me the information, potentially I have to do an error correction step. Again, this is relatively convenient to do with trapped ions. And the reason there is that, as I mentioned before, we have coherence times on the order of 100, 200, 500 milliseconds. But in order to distinguish the state, like are you bright or dark, it takes like a millisecond or half a millisecond. So we can notably faster figure out the state and what the coherence time is in the system. So what we do is you have some kind of operations. We first of all have to make sure that we only detect the ions that we care about. So we do some hiding spectroscopically of some of the qubits we don't want to project. We do a detection, we unhide the remaining qubits, we can do some correction step, and we can go on. And we recently looked into alternatives. Let's say the undercomer is a great device, but extracting information is relatively slow. So that's on the order of about 3 milliseconds. And we've been looking at Nuvo, where we can extract the information notably faster. And what you can see here is that now the camera can actually extract information faster than what it takes us to do this entire stabilizer mapping, where you have to use a couple of CNOTs and so on. And in that sense, there are also these in-sequence measurements in the register, as well as a qubit reset, can be implemented as we move along in the system size. Which brings us to the last part, like how many qubits can you conveniently work with? And so just one of the measures you could use. So it's you pick a couple of ions, how many can you entangle? And here you see the performance versus register size, and for instance, this threshold to ensure that all qubits are entangled when you use a chipset state is still met at 24 qubits, which means this fifth challenge in terms of like routinely work with ideally 16, but maybe 16 to 20 qubits, highly connected in sequence fidelities readout, all of that has been achieved. Okay, that's what we did. So like in terms of the device capabilities. And now the only thing under quotation marks that remains to be done is, well, combine everything and actually run these circuits. So here again, as a reminder, you'd have to start with, let's say you do your non-fault tolerant encoding of your logical 0, and then you want to do this verification step and ensure that your flag properly tells you, yes, there might be an error that is, let's say, too bad, not compatible with error correction, please discard or not. So we implemented that, and I think the real focus should be on the top right in this case. So what you can see here is in terms of distance, like which errors you have. Ideally, in a perfect world, everything should be like there is no error at all. That would be unreasonable, like the device is not perfect. You will have some errors, but ideally for this code, for this 7-qubit color code, you are at most allowed to have a single error. And you are not allowed to have 2-qubit errors, and you're not allowed to have 3 errors in your system. And so what you can see is the yellow is everything from this non-fault tolerant state preparation, and the green bar is what happens if we use this verification step and really check and discard data systems where we know this can't be corrected. And as hoped for, these distance 2 errors that you can't correct for usually, or like with that system with that number of qubits, these essentially vanish. So previously they've been here at about 10%, and they go to a negligible, let's say 1 to 3% level. And that's exactly what you want to have. Now you can say, now you could do a correction step and you call it a day, you're done. And the other thing which we found astonishing, well, it's ideally as expected, there are 2 colors, which means you can see a dark greenish and a bright green, and as well as a dark orange and a bright orange. Where the dark part is data from the lab, and these brighter colors are data solely based on a simple model from the system, which means to a very, very, very large degree, the entire performance of the system can be predicted from simulations, which means the noise model and everything is, let's say, well behaving. There is nothing that we currently, or like very little that we don't cover in terms of noise model compared to the real device. So once we had that and this verification step in terms of don't have more than a single qubit error working, we looked at different input states and applied the Cliffords. And as you can see here, essentially for everything that we're doing, the error rates is on the level of, say, a little bit more than 1% for all these different cardinal states of your logical qubits. Then that was great initial news. The next thing you want to push for is you have to have a CNOT, and you have to have this logical CNOT, which means here you want to work on having actually 7 CNOTs from the top to the bottom with the additional flags and so on, to make sure that each and every time when you used your initial non-fault tolerant logical 0, you add the verification step, you add various Clifford gates on the logical qubit, and then the CNOT, check what the output infidelities are. And here you can see for various input states, the output infidelities, which are on the order, again, of, for these states, 5%, and here on the order of 20%. And here, for instance, can see a logical Bell state, which was realized, for instance, with this plus 0 input state, and then you apply the CNOT. And all of that, again, works nicely. Which brings us to the hard part. Now you want to realize magic states. And as you've seen before, this circuit, it's not something that you just write down easily, but luckily, yeah, Goto, Heirat, and so on, in combination with Marcus, they were all working on that. So we could build on these tremendous years of work. So you start off with your initial state, which is encoded non-fault tolerantly. You do this Hadamard measurement. You then subsequently do this error detection to check that everything is fine. And again, here as a measure of let's say, performance, we look at this infidelity. What you can see initially when you just do this non-fault tolerant encoding, there are error rates on the order of about 9%. And if you then add this Hadamard measurement, which is essentially like a check, are you in the right subspace? The error rates ideally go down. This is exactly what we see. And if you now do an additional step on the error detection, then you can see that these error rates drop to this, let's say, roughly 1% level. And so this magic state can be realized with really, really high fidelities at that level. Which brings us to the last part. So if you want to do something like the T-gate on your logical qubit, you start off with your magic state. You start off with your logical 0. You then teleport your system, like you teleport your T-gate onto this logical qubit, and you check whether everything works as expected. And here you see infidelities on the order of 8%, and for some reason which we currently don't understand well, this one is significantly better. Like the simulation, okay, that's, but like our intuitive feeling is not so good. Where here we see infidelity on the order of 4%. And with that, we have implemented now this T-gate also on a logical qubit. And that means we have combined everything that we need. We can do Clifford gates on our logical qubit. We can do the CNOTs and so on between two logical qubits. And that demonstrates how you do a T-gate. And with that, we have completed the universal gate set. And that means we have also combined everything for universal logical gates on logical qubits. At that point, I want to highlight the two main, say, persons in the lab, or let's say brains also behind the work. So on the experimental side, it's Lukas Postler in Innsbruck, and then it's Sascha Heusen working together with Markus Müller in Jülich, and everything that we've demonstrated here can be found also on our archive paper from November last year. And with that, I'd like to thank you for your attention. So we have an international team and a couple of experimentalists in Innsbruck. As I pointed out in the beginning, okay, we like to implement the gates and everything, but we also heavily depend and like to work with theorists. So here you see Richard, Nico, Jens, Peter Zoller, Markus Müller, Miguel Angel, Joe Emerson. There should be also Joel Wallman, a couple of other colleagues that we all happily work with. If this is something that gets you, let's say, motivated and hyperly interested in either the experimental work, also, let's say, contributing new ideas of what can be done on our devices, I kindly invite you to reach out to me. And with that, I'm actually pushing towards a longer section on questions and discussions.
Great, thanks very much, Thomas, for thanks very much for a great talk. There's a slight delay in terms of the live stream versus where we are, so it may take a little bit of time for people to come in with their questions. But so maybe in the meantime, what I'll ask is, could you talk a little bit about kind of future milestones in terms of the prospects for like doing fault-tolerant gates between, say, qubits that are maybe further apart, or being able to do sequential gates at thresholds?
So there are two things which I'd say what we're going to push forward next. And we've colleagues, be that our colleagues at Google, but also Maryland and others, what we want to push for as one of the next parts is repetitive error correction on the logical qubit. So that you show if you do it again and again, it actually makes things better and not worse. Because it's a little bit, I would say it's like going to the doctor. Well, if you go to the doctor every day, there is bound to be some false positives. And so you have to do this trade-off between how, like, given the performance of your device, how often should you do error correction to actually be beneficial? So the errors need to be a little larger than what your, let's say, correction potential induces. This is something that we're also working with Simon Benjamin in Oxford in terms of like support how to do that. And his infamous Igor, whoever knows Simon Benjamin. So that's what we want to do on in terms of, let's say, repetitive error correction. The other thing which is interesting, and I think Google did it in the context of the normal repetition code, is to show larger and larger logical qubits. To say now this was with 7 qubits, go to 15, go to 20 qubits in a color code, and show that as the size of your logical qubit grows, that it becomes more and more resilient against errors. So in our case, with the 7 qubit, at most it can, let's say, compensate for a single qubit error. But as we make this logical qubit larger, we ought to be allowed to have more than one error in the register. And this is ongoing work from us and others to really demonstrate that as we go for more qubits, the systems become more resilient. And once ideally this logical qubit has sufficiently high error rates, or let's say small error rates, then we can try to implement harder and harder quantum algorithms again.
Great, thanks.
Was that what you meant with, let's say, more distance? Like there was distance code, not physical.
Yeah, no, not distance in codes, but actually physical distance of.
Okay, that's okay. Now that's fine as well. So what we're currently working, that there are also some research directions. In order, if you add more and more ions, the string becomes heavier and heavier. And so to use the motion of the ions, which is used as a data bus, which like the initial ideas from Peter Zoller. If you use that and the register becomes longer, it becomes harder and harder to really get good gates going. And so what you want to have is, first of all, longer chains, but you need to be able to split them off in smaller chunks and really make sure that you work only on those smaller registers, but still connect them somehow. This is something that we are working on together with colleagues at ETH, for instance, Jonathan Holm or Ferdinand Schmidt-Kaller with Uli Boschinger in Mainz. And one of the ideas there is not just to push for, let's say, chains in 1D, but actually also prepare, similar to our colleagues, for, let's say, the neutral atom community. They say Michel Lukin, Chunye, or Emmanuel Bloch, towards can we have 2D arrays of trapped ions to really push for significantly larger register sizes.
And just to remind you, so people can, there's a delay, so I'm not sure how this is going to work, but people can put more questions in the chat. And if we don't get them in time, we'll maybe move to the Zoom. But so maybe I can also just ask you, as you try and scale up, do you think you will, can you talk about, are you going to need to use different kinds of error correcting codes? And do you have a sense in which that may change as you try and scale up?
So what I think currently, it makes sense from a theory point of view to pick a simple model. Like if you think about the color code and most of the other code, most codes are assuming symmetrical noise. So it's like mainly your system is subject to, say, depolarizing noise, X, Y, Z, all happens the same way. But on the microscopic level, at least in our case, we are notably more dominated by dephasing and not actually depolarizing. And so it might be interesting to say, can I have some slightly asymmetric codes which is, let's say, geared towards you have, say, a factor of 5 or 10 or whatever, more dephasing noise than say it's spontaneous decay or so in the system than the XY errors. But I think that will be interesting as the systems grow, whether we want and need them, because on the other hand, as you have your system and you constantly do operations on the register, essentially you're twirling around your noise anyway. So if you think about all this randomized benchmarking, randomized compiling, optimal control work, most of the time at the end, we see something like effective depolarizing noise. So it could be that we don't really need that, and it's better to aim for still symmetric codes. On the long run, probably the most convenient way would be if you could have codes where you can adapt, like think about it like a knob. You can adapt the code on the fly, where you'd say, yesterday I had kind of symmetric noise. Today I notice I have a little bit more dephasing. So I just adapt the code a little bit more for the other noise. It's like, yeah, whatever the weather is like, you can more easily adapt the code for the predominant noise sources in your device.
Thanks. So I'm going to suggest, because of the delay, that we move, if people want, we can move to the Zoom if people have any questions or maybe just want to hang out and chat. The Zoom will be open in about, I think, 10 minutes. So we can have a little bit of a break now and people can meet there. Does that sound good? So I guess there's no way people can clap in their virtual sessions, but Thomas, thanks very much for the talk. It was very interesting.